In this example, you have a crane. Let's say you are sitting at point O here inside the crane. The crane is rotated at a constant angular velocity omega 1 here, which is equal to 0.3. So the vector format will be equal to 0.3 counterclockwise in the y direction, give you z direction. If this is rotated in opposite direction, which is in the clockwise direction to the y-axis, then you should obtain negative z direction. So you raise the boom here with constant angular velocity omega 2, which is in this direction, counterclockwise to the z-axis, and the value is given by 0.5. The vector of the omega 2 will be in the same direction with the z-axis, therefore you have k direction here. So this is the vector format for omega 2. Imagine that the initial position of the boom is here. So after you rotate it with omega 2, it will move and rotate to the current position at angle equal to 30 degrees here. The length of the boom is equal to 12 meter, so which is from 0 to P. So the magnitude of OP will be equal to 12. So if you want to find the vector for OP, then you need to take the magnitude cos with the angle, means the 12 cos 30 degree, give you the vector in x direction, which is I direction, plus the magnitude 12 sine with 30, which is the displacement vector in the z direction, because you have y direction here. So these are the displacement vector for the OP. So if you take this x component plus the y component, you obtain the displacement vector here, which is the OP vector. Imagine that you are at point O here and observe the movement for the tip of the boom here, which is at point P. You observe the boom is rotated with omega 2. Therefore, omega 2 is the omega body that you learned before. So we just simplify it as omega. We use this symbol to indicate the omega body, which is equal to 0.5 k. So this is the angular velocity that you measure from the O, which is non-inertial frame. Because you can see at point O, it is rotated with omega 1 as well. So this is the rotating frame. And we use the ohm symbol to indicate the angular acceleration for the rotating frame. Make sure you know how to differentiate which one is the angular velocity for the body and which one is the angular velocity for the frame, and use the corresponding symbol to indicate the difference between them. And normally we use the symbol R to indicate the displacement vector. So since you are pointing from O to P, so we are writing the R P with respect to O. In this problem, we are going to determine the angular velocity of the boom. You need to be careful, the angular velocity of the boom here is not equal to 0.5, because this value is a relative value, which is measured from non-inertial frame due to the rotating frame here. In fact, we want to find the absolute angular velocity of the body, which is the boom in this problem. This is actually equal to the omega total that you learned before, which can be computed by using the ohm plus the omega. So after you substitute the ohm 0.3J inside plus the omega here, then you should be able to obtain this answer. So this is absolute value. which is valid in the inertial frame, and this is what we want. Then you want to find the angular acceleration of the boom. So for the angular acceleration for the body with respect to O here, which is a rotating frame, is equal to 0 because the omega is constant in this case. So this is relative value. Angular acceleration for the frame ohm dot here is equal to 0 because the ohm here is constant. You should know that the absolute angular acceleration of the boom is equal to the omega dot total formula that you learned previously, which is equal to ohm cross with the omega. And the omega can be either omega body or omega total. For simplicity, we just use the omega body, which is equal to 0.5. So you need to perform the cross product, substitute the ohm inside, which is 0.3J. Other component you have 0, and then you have omega equal to 0.5K. After you perform this determinant, you should obtain 0.15I. So this value is an absolute value and is the angular acceleration of the boom. So far you have recognized the motion for the boom here is under the rotation at fixed point O. And you have success to obtain the angular velocity for the frame and the body to be this answer. Due to the constant angular velocity, you obtain the angular acceleration equal to 0 for the frame as well as the body. So this is the direction for the ohm, and you obtain the ohm dot equal to 0. And this is the direction for the omega, and the omega dot is 0 as well. Also, you success to obtain the displacement vector from O to P, which is over here. So this is equal to this answer. And you success to use the ohm plus omega and ohm cross omega to compute the total angular velocity and total angular acceleration of the boom. Next, we want to know the velocity of the tip of the boom, which is over here. So what is the velocity at point P? So by using the relative motion approach, the velocity at point P that is measured in the capital X, Y, Z, which is the inertial frame, is equal to the velocity at point O that is measured from the inertial frame as well, which is located here, plus the velocity of P here that is measured with respect to O. So imagine you are here, you observe the velocity at P with respect to U. Since the frame here can be rotated, therefore you are in the rotating frame. So you have small letter X, Y, Z here to indicate the rotating frame or non-inertial frame. Lastly, you have the velocity due to the rotating frame, which is equal to the ohm crossed with the radius from P with respect to O. So you have the ohm equal to 0.3 here, and you have the Rp/O equal to this value. So substitute inside, you should be able to obtain the velocity due to the rotating frame effect. Then you should be able to solve this component. If the crane is moving forward in the x-axis with 5 meters per second, then the velocity at point O here will be equal to 5I. However, in this case, the crane is not moving at all. So you have 0 value here. To compute this component, you need to imagine yourself at O, which is the non-inertial frame here. So you observe the movement of P with respect to U at O. So you can see that the rotation is due to the omega 2, which is this. Omega 2 is the omega body that we mentioned before. Therefore, we can use the symbol omega cross with the corresponding displacement vector, which is Rp/O. So you can substitute the omega information inside and the displacement vector inside. Then you can solve this component. So take the summation between these two components. You should obtain the velocity at point P to be this answer. And you can use this bracket symbol to indicate the vector. But don't forget the comma to separate between the ijk components. You can further obtain the magnitude of the velocity by taking the square root of -3 power of 2 plus 5.195 power of 2 plus -3.117 power of 2. Solve it, then you should obtain the final answer of the velocity at point P. Although we do not cover the general motion approach in this study, however, you should know if you compute the Vp using this formula, you should obtain the same answer. So this is out of the scope. Lastly, you want to find the acceleration A of the tip of the boom, which is at point P here. So the acceleration at point P that is measured with respect to the inertial frame will be equal to the acceleration at point O here with respect to the inertial frame XYZ plus the acceleration at point P measured with respect to point O. So imagine you are here and you know that this is non-inertial frame because the frame is rotating with O. Therefore, you use small letter XYZ and then you have the rotating effect. For the first term, acceleration at point O here, so if the crane is moving forward with 5I, so this is the velocity. So if the velocity keep increasing over the time, therefore you have acceleration. Let's say the acceleration is equal to 2I. So in this case, you need to substitute 2I to this component. If the velocity is reducing over the time, then you have deceleration, and the acceleration vector will be in opposite direction to the velocity vector. So you have the A equal to -2I here. So if this is the case, then you need to substitute -2I for this scenario. In this case, since the crane is not moving, therefore the velocity and acceleration will be equal to 0 in this case. So if you substitute 0 inside, you obtain 0 acceleration for this component. Since the boom here is rotated with omega, when you observe the movement of point P with respect to point O here, then you see the object move tangential in this direction. So the acceleration in this tangential direction is equal to angular acceleration for the body, which is equal to 0 due to the constant angular velocity for the body. So the acceleration component in the tangential direction is the angular acceleration of the body crossed with the radius P with respect to O. So since this component is 0, when you cross it, you obtain this acceleration component equal to 0. Due to the rotation of the body, you will also have the acceleration in the normal direction here. So you can obtain the acceleration component in the normal direction to be omega body cross with the omega cross with the displacement vector p with respect to O. This component is calculated previously. We can substitute the answer from here. So you can also substitute the omega body to this and then compute the cross product between these two components. Then you should be able to obtain the result. So together, the summation between these two components, one is from the tangential direction, another is from the normal direction here. So together, summation, you obtain the final answer for AP/O here. You have three additional acceleration components due to the rotating frame effect. The first two formula here is similar to these two formula, where you change the omega dot into ohm dot and omega into ohm. So you should obtain these two acceleration components. One is the tangential acceleration, another one is the normal acceleration. The last acceleration component is the Coriolis acceleration, which has 2 ohm crossed with the velocity of p with respect to O. Since O here is non-inertial frame, therefore we use the small letter xyz. These are the three acceleration components due to the rotating frame effect. Where you can see all of them has the ohm or ohm dot. So you can substitute the ohm into this formula. Ohm dot should be equal to 0 because the ohm is equal to constant. Therefore, this can be cancelled. So this acceleration component is equal to 0. And then you can substitute the RP/O here inside. So this term, you need to perform first. In fact, you have performed this component before. So you can just substitute this answer inside. After you substitute the answer from the velocity equation that you compute previously, you need to take the vector product between the ohm crossed with this component. Then you should be able to obtain this acceleration component. Lastly, you need this component to compute the Coriolis acceleration. Luckily, you have computed this before in the velocity equation. So this is equal to omega cross RP/O, which gives you this answer. So we can substitute this value inside. After you substitute inside here and take the cross product between this component and this component, then you can get the Coriolis acceleration. So this is 0 as well as these two components. So we can cancel it. And this component is divided into these two components already. So we can take it out. So in total, you only have 3 acceleration components. Take the summation for all of these acceleration components, then you should be able to obtain the acceleration at point P. These are the steps that we described earlier. You should be able to obtain the result for the remaining acceleration component here. Take the summation of it, you should obtain this answer. And you can obtain the magnitude from this vector by using the formula square root of the x magnitude square plus the y magnitude square plus the z magnitude square. So you should obtain this magnitude for the acceleration at point P, which is the tip of the boom. So you should master the relative motion approach to solve 3D kinematic problems like this case. So you have arm OA from here to here, given by 0.8 meter length. There is a control mechanism system which is rotate about the horizontal x-axis of the crevice. There is a control mechanism here, pivot about the horizontal x-axis of the crevice. So this is the control mechanism which is pivot in the x-axis. The entire assembly rotates about the z-axis with a constant speed n equal to 60 revolutions per minute. So this is the direction for the n. So the omega is in this direction because this is in counterclockwise with respect to the z-axis. So your omega will be in k direction. However, you need to convert the unit for the n to the radian per second. So the n is equal to 60 rpm, and you can convert it into radian per second by multiply 2 pi divided with 60. Since 1 revolution you have 2 pi radian and 1 minute you have 60 seconds. You should obtain around 6.3 radian per second. So your first omega is equal to 6.3 in the k direction here. Simultaneously, the arm here from O to A is being raised at a constant rate beta dot equal to 4 radian per second. So you must know the OA arm must be rotated counterclockwise to the x-axis here in order to raise the arm. So you should obtain the angular velocity is equal to the I direction and the magnitude is equal to 4 here. So you have two angular velocity here. So which one is the angular velocity for the frame and which one is angular velocity for the body? To identify this, the easiest way is you imagine yourself at point O here and look at the movement for A. So you see the movement A is due to the omega 2 here. So this is the angular velocity for the body here. So we can say the omega body is equal to 4i. And due to the rotation here, this guy is rotating. So the omega 1, which is the 6.3k, is equal to the ohm. This is the angular velocity for the frame. Since it mentioned that both of them are constant, therefore you know the ohm dot and omega dot will be equal to 0. Since you have rotating frame, therefore the guy standing at point O here is no longer a inertial frame. This is non-inertial frame or rotating frame. To find the displacement vector RA with respect to O, which is here, you need to project it to the XYZ direction. So if you project to this direction, you have the y-axis. So y component is 0.8 cos 30. And if you project to this direction, you obtain the z component, and this is equal to 0.8 sine 30 degrees. So if you project to x-axis, you obtain 0. Therefore, this component will be in j and k direction only. You should obtain this result. What is the omega total? You can obtain by taking the summation of ohm plus the omega. What is the angular acceleration? Which is the omega dot. So you can take the ohm cross with the omega. After you calculate these two components, you should obtain these two answers, and this is the answer for A, which is the angular velocity of OA, and angular acceleration of OA, which is in absolute value. And then you need to find the velocity and acceleration of point A here. So you must learn how to use the relative motion approach to form the equation here. So the velocity of A here is equal to velocity at O plus the velocity A with respect to O, and the O here, this guy, is at the small letter XYZ, which means this is non-inertial frame. So if you have non-inertial frame, you have the rotating frame effect here. So the point O doesn't move, therefore there is zero translation. So this component can be cancelled. So you can solve this component by substitute the ohm and the RA/O inside and perform the cross product. To compute this velocity component, you need to imagine yourself at point O here and look at point A. So the motion of point A is rotate due to the omega here. Therefore, the velocity due to the omega is equal to the omega cross R. And the R is A with respect to O. So you can substitute the omega for the body inside as well as the displacement vector here. Then you can obtain this value. So after you take the summation of all the velocity components, then you're able to obtain the absolute velocity at point A. And you should get this answer. Similarly, you can obtain the acceleration at point A, which is equal to the acceleration at point O here, plus the acceleration of point A with respect to point O, and O is at the XYZ small letter of it to indicate the non-inertial frame. So this is called the sliding acceleration. Additional 3 acceleration component here is due to the rotating frame effect, where you can see all the angular velocity is from the ohm and ohm dot. Since point O doesn't move, there is zero translation, therefore this term can be cancelled. The tangential acceleration is equal to 0 as well because the ohm dot is 0 in this case due to the constant ohm. So in this example, this term can be cancelled and we continue with this term. So the normal acceleration, you need to compute the vector triple product. So you have computed this component previously over here. So substitute inside and perform the cross product between these two components. Then you can obtain this acceleration. This component has been calculated before as well, so you can substitute inside here. So take the cross product between these two components, then you can obtain the Coriolis acceleration. Lastly, for this component, you need to imagine yourself at the point O at the rotating frame here. And you observe the acceleration at point A here. Since the OA is due to the omega, therefore there is tangential acceleration and normal acceleration due to the rotation. So you can obtain the acceleration in the tangential direction and the normal direction. Basically, the formula are similar to these two, where we just replace the ohm dot into omega dot and ohm into omega due to the rotation of the body. Since the ohm and the omega have constant angular velocity for the frame and the body, therefore the ohm dot and the omega dot, which is the angular acceleration for the frame and the body, will be equal to 0. So these two acceleration components can be cancelled. So you have computed this component before, you can substitute inside here and take the cross product between the omega and this component, and you should be able to obtain this acceleration component. Compute the summation for this acceleration component, then you should be able to obtain the acceleration at point A, and this is the answer. Lastly, the vertical shaft and point O here had linear motion, let's say in the z direction. The question asks if the motion will change the angular velocity or the angular acceleration of OA that you obtained before here. Since we are computing the total angular velocity and total angular acceleration by using this formula, it is only depending on the ohm and the omega. It does not depend on the velocity at any point here. Therefore, this result will be remain. What if the linear shaft here and point O is moving upward with velocity equal to 10 in the z direction, which is k, and the acceleration is negative 5 in the k direction? Would this change the velocity at point A and the acceleration at point A here? The answer is yes, because when the shaft and point O is moving upward, the velocity at point O here is no longer equal to 0. It will be equal to 10 for the velocity and it will be equal to negative 5 for the acceleration. Therefore, we need to substitute the velocity and acceleration at point O here into these two components. So you need to substitute it inside the equation and recompute the velocity and acceleration at point A. You should have better idea now how to use the relative motion approach to solve the 3D kinematic problem like this case. Practice yourself to use these two equations and see if you can get the correct answer here.